700 million years after creation, something impossible lurks in darkness. A monster 50 million times heavier than our Sun floats naked in space, with no galaxy to call home. The James Webb Space Telescope caught a black hole that shouldn't exist, breaking every rule governing the infant universe. We're about to journey through discoveries that rewrite cosmic history. You'll witness gravitational lenses, bending spacetime, meet primordial monsters from the Big Bang, and discover how empty space hides the universe's violent secrets. If you're ready to see how one red dot changed everything about creation, hit subscribe and prepare for impossible. 700 million years after the Big Bang, when our universe was still an infant, something appeared that defied every law of cosmic evolution. The James Webb Space Telescope, humanity's most powerful eye into deep space, detected a tiny red dot floating in the ancient darkness. Scientists initially dismissed it as another distant galaxy, nothing special among billions of similar objects scattered across the cosmic web. But when astronomers aimed their instruments directly at this crimson speck, they discovered something that made their blood run cold. The dot wasn't behaving like a normal galaxy at all. Its light signature contained mysterious broad hydrogen lines, suggesting violent motion happening at incredible speeds. Gas clouds were spinning so fast they should have been torn apart by centrifugal force, yet somehow they remained intact. This was confirmed through spectroscopic analysis, revealing rotation velocities that reached thousands of miles per second. No ordinary stellar system could generate such extreme motion without destroying itself completely. The discovery team, led by researchers at Cambridge University, realized they were witnessing something unprecedented in cosmic history. What makes this red dot truly terrifying is its location in spacetime. We're seeing it exactly as it appeared when the universe was barely 5% of its current mass concentrated into a region smaller than our solar system, creating a gravitational well so deep that light itself barely escaped its clutches. The implications sent shockwaves through the astronomical community. If such massive black holes existed when the universe was practically newborn, then everything we believed about cosmic evolution needed immediate revision. These weren't gradual formations built up over eons. They were primordial monsters, born fully formed in the cosmic dawn. Dr. Roberto Maiolino, one of the lead researchers, described the discovery as completely off the scale of known physics. The team had stumbled upon what appeared to be a naked black hole, existing without the typical galaxy structure that should surround such massive objects. But what they found next would prove even stranger than a monster floating alone in ancient space. The detailed analysis revealed something that challenged the very foundations of how we understand reality itself. What comes next defies not just physics, but imagination itself. The only reason humanity can peer into this cosmic mystery lies in a fortunate accident of celestial mechanics. Between Earth and the ancient red dot sits a massive galaxy cluster, its gravitational field so intense that it bends space-time itself like a cosmic magnifying glass. This phenomenon, called gravitational lensing, acts as nature's own telescope, allowing us to see objects that would otherwise remain invisible across such vast distances. Einstein predicted this effect in his theory of general relativity over a century ago, but he never imagined it would become our window into the universe's darkest secrets. The cluster's gravity doesn't just bend light, it amplifies it by factors of 10 or more, transforming a barely detectable smudge into something JWST can analyze in stunning detail. Without this cosmic coincidence, the monster would have remained hidden forever. The lensing effect creates multiple images of the same object, appearing as bright arcs stretched around the foreground cluster. Astronomers call this configuration the cosmic horseshoe, and it represents one of the most perfect gravitational lenses ever discovered. Each image shows the ancient black hole from a slightly different angle, providing unprecedented three-dimensional information about its structure and behavior. This natural telescope revealed something that left scientists speechless. The background object, designated QSO-1, wasn't just massive beyond comprehension. It was actively feeding, consuming matter at rates that pushed the theoretical limits of physics. Streams of superheated gas spiraled inward at velocities approaching the speed of light, generating radiation signatures never before observed in the early universe. The team spent over 40 hours collecting spectroscopic data, confirmed through multiple independent observations using different instruments. Every measurement pointed to the same impossible conclusion. They were witnessing a black hole with mass equivalent to 50 million stars, existing when the cosmos was barely 700 million years old. The gravitational lensing magnification allowed them to measure this mass directly, removing any doubt about the monster's true nature. But the lensing revealed something even more disturbing than the black hole's size. The surrounding environment appeared almost completely empty of stars. Normal galaxies contain billions of stellar objects, creating a characteristic glow that should be easily detectable even at such extreme distances. Yet QSO-1 showed no such signature, floating naked in the cosmic void like a solitary predator stalking empty space. Dr. Ignace Juodzbalis, who led the detailed analysis, described the discovery as finding a monster that shouldn't exist in a place where nothing should live. The gravitational lens had exposed not just an impossible object, but an impossible situation that challenged fundamental assumptions about how the universe assembled itself during its earliest epochs. The precision measurements made possible by lensing magnification would soon reveal the most shocking aspect of this cosmic enigma. The numbers they calculated would rewrite the textbooks of reality. When astronomers calculated the final mass measurement, the number staring back at them seemed like a cosmic joke. 50 million solar masses concentrated into a region no larger than our solar system. To grasp this magnitude, imagine cramming 50 million copies of our Sun into the space between Mercury and Neptune. The gravitational field would be so intense that time itself would slow to a crawl near the surface. This confirmed measurement came from analyzing the rotation curve of gas orbiting the central object. As matter spirals inward, it follows precise Keplerian orbits, determined entirely by the central mass. By measuring how fast this material moves at different distances, scientists can calculate the mass of whatever lurks at the center with extraordinary precision. The calculations were unambiguous and terrifying. For comparison, the supermassive black hole at our galaxy's center weighs about 4 million solar masses and took over 13 billion years to reach that size. Yet here was an object more than 12 times more massive, existing when the universe was barely 5% of its current age. The formation timeline made no physical sense according to any known process. The mass ratio, compared to its host environment, defied every rule of galactic evolution. In normal galaxies, the central black hole represents roughly 1/10% of the total stellar mass. But QSO-1 appeared to contain at least 10% of its entire system's mass, possibly much more. Some calculations suggested the black hole might actually outweigh everything else combined, creating a cosmic situation never before witnessed. This extreme mass concentration created observational signatures that confirmed its black hole nature beyond any doubt. The event horizon, that point of no return where gravity becomes inescapable, stretched across a diameter larger than our entire solar system. Any matter crossing this boundary would be lost forever, adding to the monster's already incomprehensible mass. The feeding rate necessary to maintain such extreme luminosity pushed against fundamental physical limits. The Eddington limit describes the maximum rate at which any object can consume matter before radiation pressure tears apart incoming material. Yet QSO-1 appeared to be operating right at this theoretical boundary, consuming the equivalent of multiple Earth masses every single second. But the most disturbing aspect wasn't the black hole's incredible mass or feeding rate. It was what surrounded it, or rather, what didn't. The gravitational lensing revealed an environment almost completely devoid of the stellar population that should accompany such a massive central object. This wasn't just an oversized black hole. It was a naked monster floating alone in primordial space. The implications struck at the heart of everything scientists believed about cosmic evolution. How could such a massive black hole exist without a corresponding galaxy to feed it? The answer would challenge our understanding of the universe's birth itself. In every corner of the modern universe, supermassive black holes hide at the centers of galaxies, surrounded by billions of stars that feed them over cosmic time. This relationship represents one of the fundamental partnerships in cosmic evolution. Galaxies provide the raw material. Black holes regulate star formation through their immense gravitational influence. It's a cosmic dance that has continued for over 13 billion years. But QS01 breaks this sacred rule completely. The object appears essentially naked, with a stellar mass so small it barely registers in observations. Conservative estimates suggest the black hole outweighs its surrounding stars by at least 2 to 1, possibly by factors of hundreds or thousands. This ratio represents something unprecedented in astronomical observations. The mystery deepens when we consider the chemical composition of the sparse gas surrounding the monster. Spectroscopic analysis, confirmed through multiple independent measurements, reveals oxygen abundance, less than 1% of what we find in our Sunday. This pristine chemical signature indicates an environment that has experienced virtually no stellar evolution. Very few stars have lived and died here, leaving the primordial gas almost unchanged since the Big Bang. This observation theory suggests we're witnessing a massive black hole in its absolute infancy, caught in the earliest possible stages of galaxy formation. But this explanation creates its own problems. How did such a monster form without consuming the very material that should have built the surrounding galaxy? The physics doesn't add up according to any standard model. Normal black hole formation requires either the collapse of massive stars or the gradual merger of smaller objects over billions of years. Both processes should leave clear observational signatures in the surrounding environment. Stellar collapse produces heavy elements that pollute the local gas. Mergers require pre-existing populations of smaller black holes, which themselves need time to form and evolve. Yet QS01 shows none of these expected signatures. The environment appears chemically pristine, suggesting minimal stellar processing. The mass concentration happened too quickly and too early for conventional formation mechanisms. Something else must be responsible for creating this cosmic aberration. The naked nature of this black hole suggests we're seeing the endpoint of a completely different formation process, one that bypasses the normal relationship between galaxies and their central monsters. Instead of growing gradually within an evolving stellar system, QS01 appears to have formed first, potentially serving as the seed around which a galaxy might eventually assemble. This inverted timeline challenges everything astronomers thought they knew about cosmic structure formation. If black holes can form before galaxies rather than within them, then the entire sequence of events in the early universe needs revision. But how could such massive objects appear so early in cosmic history? To understand the true impossibility of QS01's existence, we must journey back to the universe's earliest moments. 700 million years after the Big Bang sounds like an eternity, but in cosmic terms, it's barely a heartbeat. During this epoch, known as the Epoch of Reionization, the universe was undergoing its most dramatic transformation since the moment of creation itself. The cosmic microwave background, that ancient light we can still detect today, shows us what the universe looked like just 380,000 years after the Big Bang. At that time, space was filled with a hot, dense soup of hydrogen and helium gas, completely dark because no stars had yet formed to light the cosmic night. This period of darkness lasted for hundreds of millions of years. The first stars finally ignited when the universe reached roughly 100 million years old. But these were not the stable, long-lived objects we see today. They were massive, violent giants that burned through their nuclear fuel in just a few million years before exploding as supernovae. These stellar deaths seeded space with heavier elements and created the first small black holes, typically weighing only 10 to 100 times our Sun's mass. By 700 million years after creation, the universe should have contained only these relatively small stellar mass black holes, and perhaps a few early galaxies containing the first generation of heavy element-enriched stars. The theoretical timeline simply doesn't allow enough time for conventional processes to build supermassive black holes weighing 50 million solar masses. This timing problem has been confirmed through multiple independent dating methods. The redshift measurement of QSO-1 places it definitively at this early cosmic epoch, with less than 5% margin of error. We're not looking at a nearby object that appears ancient. We're genuinely witnessing the universe as it existed when cosmic history had barely begun. The formation rate required to build QSO-1 by conventional means would require consuming the equivalent of 1,000 Earth masses every single year for the entire 700 million year period since the Big Bang. But the early universe simply didn't contain enough concentrated matter to fuel such extreme growth rates, especially in the pristine environment we observe around the monster. Even more puzzling is the fact that QSO-1 appears fully mature despite its extreme youth. The object shows all the characteristics of a stable, well-developed black hole operating at peak efficiency. There are no signs of the chaotic, irregular behavior we might expect from a rapidly growing object still in its formation phase. This maturity suggests the black hole didn't gradually assemble over cosmic time, but instead appeared as a fully formed monster very early in universal history. The implications point toward formation mechanisms that challenge our understanding of physics itself. QSO-1 isn't alone in its cosmic impossibility. Since JWST began peering into the early universe, astronomers have discovered over 300 similar objects scattered across the ancient sky. These mysterious sources, dubbed little red dots by the scientific community, share the same puzzling characteristics that make QSO-1 so enigmatic. Each one defies explanation through conventional formation theories. The red coloration comes from their unique spectral signatures, confirmed through extensive photometric analysis. Unlike normal galaxies that emit light across a broad spectrum, these objects show pronounced emission in specific infrared wavelengths that appear red-shifted due to cosmic expansion. This distinctive signature allows astronomers to identify them even at the most extreme distances observable by current technology. Statistical analysis of the little red dot population reveals a pattern that troubles cosmologists. These objects appear 10 to 100 times more frequently than theoretical models predict for the early universe. If each represents a massive black hole system like QSO-1, then the infant cosmos contained far more monster black holes than should have been physically possible through normal formation channels. The distribution across the sky appears random, suggesting these objects formed through processes that operated uniformly throughout the early universe rather than in special, rare environments. This widespread occurrence makes the formation mystery even more perplexing. Whatever created QSO-1 wasn't a unique cosmic accident, but a common phenomenon during the universe's first billion years. Spectroscopic follow-up observations of multiple little red dots have confirmed that many contain broad hydrogen emission lines, the telltale signature of rapidly rotating gas around massive central objects. The line widths indicate orbital velocities consistent with black holes weighing millions to tens of millions of solar masses. Each discovery adds another impossible monster to the growing catalogue of early universe enigmas. But these objects show remarkable diversity despite their common red appearance. Some, like QSO-1, appear essentially naked with minimal surrounding stellar populations. Others seem embedded within more substantial galaxy structures. though still with unusual mass ratios compared to modern systems. A few show evidence of active feeding, consuming matter at rates that push theoretical limits. The chemical compositions vary significantly between different little red dots, ranging from the pristine environment around QSO-1 to systems showing evidence of substantial stellar processing. This diversity suggests multiple formation pathways may have operated during the early universe, each producing slightly different types of massive black hole systems. Most intriguingly, some little red dots appear to be caught in the process of merging with neighbors, potentially growing even larger through gravitational interactions. These merger events provide direct observational evidence of black hole growth mechanisms operating in the ancient cosmos. But among all these cosmic mysteries, QSO-1 remains the most extreme example of something that shouldn't exist. The breakthrough that definitively identified QSO-1 as a massive black hole came from measuring how gas moves in its immediate vicinity. Using JWST's unprecedented infrared capabilities, astronomers mapped the velocity of material at different distances from the central object, creating what scientists call a rotation curve. This technique has revealed some of the most important discoveries in modern astrophysics, from dark matter to supermassive black holes. The measurements required extraordinary precision, confirmed through multiple independent observations over several months. Each spectroscopic data point revealed gas clouds moving at specific velocities, following the predictable patterns of objects in gravitational orbit. The closer to the center, the faster the material moved, exactly matching the signature of Keplerian motion around a massive central mass. At the innermost detectable regions, gas reaches velocities exceeding 2,000 miles per second. These extreme speeds can only be sustained by gravitational fields generated by incredibly dense objects. Normal stellar systems, even the most massive star clusters, couldn't produce such intense gravitational acceleration without immediately flying apart under centrifugal force. The rotation curve analysis ruled out alternative explanations with mathematical certainty. Some astronomers had proposed that little red dots might be unusually dense star clusters rather than black hole systems, but stellar clusters follow different velocity patterns, with much lower central concentrations and broader velocity distributions. The QSO-1 data showed none of these characteristics. Instead, the measurements perfectly matched theoretical predictions for a point mass containing 50 million solar masses worth of material. The agreement between observation and theory left no room for doubt about the object's true nature. Whatever lurks at QSO-1's center, it behaves exactly like a supermassive black hole operating according to the laws of general relativity. But the rotation curve revealed something even more startling than just confirming the black hole's presence. The velocity measurements extended far enough from the center to detect the gravitational influence of surrounding stellar populations. In normal galaxies, this region should show the combined effects of both the central black hole and billions of surrounding stars. Yet, the QSO-1 rotation curve showed almost no evidence of additional stellar mass. The measurements remained consistent with a single central point mass throughout the observable region. Either the surrounding galaxy was incredibly compact, concentrated within an impossibly small volume, or it simply didn't exist in any meaningful sense. This observational evidence transformed QSO-1 from just another massive early black hole into something unprecedented in cosmic evolution. Here was a 50 million solar mass monster, floating essentially naked in primordial space, with no significant stellar population to explain its formation or continued existence. The implications demanded a complete rethinking of how such objects could come to exist. In 1971, physicist Stephen Hawking proposed one of the most radical ideas in cosmology. He suggested that black holes didn't have to form from collapsing stars or merging smaller objects. Instead, they could have been created directly during the Big Bang itself, born from primordial density fluctuations in the first microseconds of cosmic existence. These hypothetical objects, called primordial black holes, remained purely theoretical for over 50 years. The formation mechanism requires extreme conditions that existed only during the universe's first moments. In the primordial fireball immediately after creation, tiny quantum fluctuations could have grown into density peaks massive enough to collapse under their own gravity. These fluctuations would have been stretched to macroscopic scales by cosmic inflation, creating black hole seeds with masses ranging from microscopic to millions of solar masses. Unlike stellar black holes that form from the cores of dying massive stars, primordial black holes could theoretically emerge with any mass determined by the initial density fluctuation. Some might weigh as little as asteroids, others could contain the mass of entire star clusters. The key difference is timing. They would have formed completely before the first stars ever ignited, existing as cosmic monsters in an otherwise empty universe. This formation pathway could explain QS01's puzzling characteristics perfectly. A primordial black hole weighing 50 million solar masses would have emerged from the Big Bang fully formed, requiring no subsequent growth or merger processes. It could exist in the pristine environment we observe, floating naked in space without any surrounding stellar population to complicate its chemical signature. The chemical composition around QS01 provides strong supporting evidence for this theory. The gas shows oxygen abundance, less than 1% of solar values, exactly what we would expect from material that has experienced minimal stellar processing. If the black hole formed through conventional stellar evolution or merger processes, the surrounding environment should show clear evidence of heavy element production from supernovae and stellar winds. Recent theoretical work has refined primordial black hole formation models, showing that certain inflation scenarios naturally produce objects in the mass range we observe for QS01. These models predict that primordial black holes should be most common at masses between 10,000 and 100 million solar masses, precisely the range where we find the most puzzling early universe objects. But primordial black hole theory faces its own challenges. The formation mechanism requires very specific conditions during cosmic inflation, and most models predict far fewer massive primordial black holes than we appear to observe. The abundance of little red dots suggests that if they are primordial black holes, then the formation process was much more efficient than most theories allow. Additionally, primordial black holes should show different growth patterns than stellar origin objects, consuming matter in ways that might leave distinct observational signatures. The evidence pointing toward this exotic formation mechanism continues to mount with each new discovery. The mystery of QS01's formation has divided astronomers into two competing camps, each proposing radically different explanations for how such massive black holes could exist so early in cosmic history. The first theory, called direct collapse, suggests that massive gas clouds in the primordial universe could have collapsed directly into supermassive black holes without ever forming stars. The second maintains that conventional stellar processes, accelerated by exotic conditions, could have built these monsters through rapid growth phases. Direct collapse requires pristine gas clouds weighing millions of solar masses to remain stable, long enough for gravity to overcome internal pressure and trigger gravitational collapse. Under normal circumstances, such clouds would fragment into thousands of smaller clumps, each forming individual stars, rather than a single massive object. But in the early universe, special conditions might have prevented this fragmentation process. The theory predicts that direct collapse black holes should form in environments with very specific chemical compositions, confirmed through spectroscopic analysis. The gas must be almost entirely hydrogen and helium, with virtually no heavier elements that could cool the cloud and allow fragmentation. QS01's pristine environment fits this requirement perfectly, supporting the direct collapse hypothesis. However, direct collapse models face a significant observational challenge. The formation process should produce intense ultraviolet radiation as the collapsing gas heats up and begins falling toward the newly formed black hole. This UV signature should be detectable even at extreme distances, yet QSO-1 shows no evidence of such emission. The absence of expected radiation patterns raises serious questions about whether direct collapse actually occurred. The alternative stellar death pathway proposes that the first generation of stars in the universe were fundamentally different from anything we observe today. These population 3 stars could have been hundreds of times more massive than our Sun, burning through their nuclear fuel in just a few million years, before collapsing into black holes weighing thousands of solar masses. Subsequent mergers between these stellar mass black holes could theoretically build supermassive objects, but the stellar death mechanism faces its own timing problems. Even under the most optimistic scenarios, building a 50 million solar mass black hole through mergers would require hundreds of millions of years. The process involves multiple generations of star formation, death, and black hole merger events, each taking substantial amounts of time to complete. Mathematical modeling shows that stellar origin black holes would need to grow at rates very close to the theoretical maximum allowed by physics. They would have to consume matter continuously at the Eddington limit for hundreds of millions of years, requiring a constant supply of fuel that may not have existed in the sparse early universe environment. The observational evidence from QSO, one may soon decide between these competing theories once and for all. It forms a swirling accretion disk that heats up to millions of degrees through gravitational friction. This superheated material should shine brilliantly in ultraviolet and X-ray wavelengths, creating some of the brightest objects in the universe. Every known active black hole in the modern cosmos follows this pattern without exception. The UV emission is so fundamental to black hole physics that astronomers use it as the primary diagnostic for identifying actively feeding black holes across cosmic distances. The characteristic spectral signature is unmistakable, confirmed through decades of observations of quasars and active galactic nuclei. Yet QSO-1 and its little red dot cousins show little to no emission in these critical wavelengths. Several exotic explanations have been proposed to account for this mysterious UV deficiency. Perhaps the black holes are surrounded by dense clouds of dust that absorb the ultraviolet photons before they can escape to space. But dust analysis of the QSO-1 environment shows insufficient material to block such intense radiation completely. The pristine chemical composition argues against significant dust formation. Another possibility suggests that these black holes are feeding in fundamentally different ways than their modern counterparts. Instead of the chaotic, turbulent accretion that characterizes normal quasars, perhaps QSO-1 is consuming matter through a more ordered process that doesn't generate the extreme temperatures needed for UV emission. But no known physical mechanism can account for such unusual feeding behavior. The most disturbing possibility is that our fundamental understanding of black hole physics is incomplete. Perhaps the extreme conditions in the early universe allowed these objects to operate according to different physical laws than what we observe today. The pristine environment, combined with the unusual mass ratios and formation timelines, might represent a completely different class of black hole behavior. Some researchers have proposed that QSO-1 might be in a dormant phase, having consumed most of the available matter in its immediate vicinity. A sleeping supermassive black hole would produce minimal radiation while retaining all of its gravitational effects. But this explanation struggles to account for the broad hydrogen emission lines that indicate ongoing gas motion and potential feeding activity. The UV mystery deepens when we consider that multiple independent little red dots show similar radiation deficiencies, despite existing in different environments and showing different chemical compositions. This pattern suggests the missing ultraviolet light isn't a coincidence, but a fundamental characteristic of early universe black holes. The discovery of QSO-1 has forced astronomers to confront a revolutionary possibility that inverts everything we thought we knew about cosmic evolution. Instead of galaxies forming first and then growing supermassive black holes at their centers, perhaps massive black holes formed first and served as the gravitational seeds around which galaxies later assembled. This bottom-up formation scenario could explain the naked monsters we observe in the early universe. Traditional galaxy formation models, confirmed through computer simulations and observational studies, describe a hierarchical process where small structures merge to form larger ones over cosmic time. Dark matter halos collapse first, then attract ordinary matter that cools and condenses into stars. These stellar populations gradually build up over hundreds of millions of years, eventually becoming massive enough to form and feed central supermassive black holes. But QSO-1 appears to reverse this sequence completely. Here we have a fully formed 50 million solar mass black hole, existing in an environment that shows minimal evidence of stellar evolution. The chemical composition suggests very few stars have lived and died in this region, yet the central black hole has already reached enormous proportions. Something created the monster before normal galaxy formation processes had time to operate. This top-down formation model solves several puzzling aspects of early universe observations. If massive black holes formed first, they could serve as gravitational anchors that help accelerate the assembly of surrounding dark matter structures. Their intense radiation fields could also regulate star formation in the surrounding gas, potentially explaining the unusual stellar populations we observe in early galaxies. The gravitational effects of primordial supermassive black holes would extend far beyond their immediate surroundings, confirmed through theoretical modeling studies. A 50 million solar mass object creates gravitational wells that can influence matter over distances of millions of light years. These extended influence zones could help explain how large-scale structure formed so rapidly in the early universe. Recent computer simulations have begun exploring black hole-first scenarios, revealing that such massive objects could indeed catalyze galaxy formation under the right conditions. The black hole's gravity helps, suggesting they must have occurred. The implications extend beyond just understanding early cosmic evolution. If supermassive black holes really did form before galaxies, then these objects played a much more fundamental role in shaping the universe than previously realized. They weren't just passengers in cosmic evolution, they were the drivers. Perhaps the most shocking aspect of QSO-1 isn't its absolute mass, but its mass relative to everything else in its immediate cosmic neighborhood. In every normal galaxy throughout the modern universe, the central supermassive black hole represents roughly 0.1% of the total stellar mass. This ratio appears to be a fundamental relationship that governs how galaxies and their central black holes grow together over cosmic time. QSO-1 shatters this rule completely. Conservative estimates suggest that the QSO-1 black hole outweighs its surrounding stellar population by at least 2 to 1, possibly by factors of hundreds or even thousands. This extreme mass ratio has never been observed in any other cosmic system, representing a complete departure from the normal relationship between black holes and their host environments. The implications challenge our understanding of how these systems form and evolve. The mass ratio mystery becomes even more perplexing when we consider the feeding requirements necessary to build such a massive black hole. Under normal circumstances, supermassive black holes grow by consuming matter from their surrounding galaxies over billions of years. The process requires a steady supply of gas and stars that spiral inward through gravitational interactions. But QSO-1 appears to have consumed everything available while somehow avoiding the formation of a substantial stellar population. Theoretical modeling shows that building a 50 million solar mass black hole should require consuming the equivalent of at least 10 billion stars worth of material over cosmic time. Yet, the surrounding environment contains evidence for only a tiny fraction of this stellar mass, if any substantial stellar population exists at all. Either the formation process was extraordinarily efficient, or it operated through mechanisms completely different from anything we understand. The extreme mass ratio also creates stability problems that shouldn't be solvable according to current physics. A naked black hole with such dominance over its environment should have consumed or ejected any remaining matter through gravitational interactions. Yet, QS01 continues to show evidence of ongoing gas motion and potential feeding activity, suggesting the system remains dynamically active despite its unusual configuration. Modern computer simulations struggle to reproduce such extreme mass ratios through any known formation pathway. Models that start with stellar mass black holes and allow them to grow through mergers and accretion never reach the mass dominance we observe in QS01. Even the most optimistic scenarios, assuming perfect feeding efficiency and unlimited matter supply, fall short of explaining the observed mass relationship. Direct collapse models fare slightly better, but still cannot account for the complete absence of accompanying stellar formation. Even if a massive gas cloud collapsed directly into a supermassive black hole, the process should have triggered at least some star formation in the surrounding material. The fact that QS01 appears essentially naked suggests formation mechanisms that bypass stellar processes entirely. The mass ratio mystery points toward physics operating under conditions we've never encountered before. The chemical fingerprint of matter surrounding QS01 tells a story of cosmic evolution frozen in time. Spectroscopic analysis reveals gas clouds with oxygen abundance less than 1% of what we find in our solar system, making this one of the most chemically primitive environments ever discovered in the universe. This pristine composition provides crucial clues about both the black hole's formation and the early conditions that shaped cosmic evolution. In the modern universe, interstellar gas carries the accumulated chemical legacy of billions of generations of stellar evolution. Massive stars forge heavy elements in their nuclear cores, then disperse these products throughout space when they explode as supernovae. Over cosmic time, this stellar processing has enriched the universe with carbon, oxygen, iron, and dozens of other elements essential for planet formation and eventually life itself. But the gas around QS01 shows almost no evidence of this stellar processing, confirmed through detailed abundance measurements of multiple chemical species. The composition remains dominated by hydrogen and helium, the primordial elements created during the first few minutes after the Big Bang. Chemical evidence also provides insight into why QS01 appears so naked compared to normal galaxies. Star formation requires cooling mechanisms that depend on the presence of heavy elements like carbon and oxygen. These elements act as cosmic refrigerants, allowing hot gas clouds to radiate away their thermal energy and collapse under gravity. Without sufficient heavy element abundance, star formation becomes extremely inefficient. The low metallicity around QS01 may explain why the system never developed a substantial stellar population despite containing enough matter to build multiple galaxies. The pristine gas simply couldn't cool efficiently enough to trigger widespread star formation, leaving most of the available matter in diffuse clouds rather than condensed stellar objects. But this explanation creates its own puzzles. How did the central black hole manage to feed and grow without the chaotic processes that normally accompany star formation? Stellar feedback typically helps drive gas inward towards central black holes, providing the fuel necessary for growth. In the absence of substantial stellar activity, alternative feeding mechanisms must have operated. The chemical purity of QS01's environment suggests we're witnessing cosmic evolution in its most primitive state. Despite existing in a chemically pristine environment with minimal stellar populations, QS01 shows clear evidence of active feeding that challenges our understanding of how black holes consume matter in the early universe. The broad hydrogen emission lines indicate gas moving at thousands of miles per second in the immediate vicinity of the monster, suggesting ongoing accretion processes that somehow operate without the chaotic stellar feedback normally associated with galaxy formation. The feeding rate necessary to maintain QSO-1's observed luminosity approaches the theoretical maximum allowed by physics. Known as the Eddington limit, this boundary describes the maximum rate at which any object can consume matter before radiation pressure from the feeding process becomes so intense that it blows away incoming material. Operating at this extreme limit suggests the black hole is consuming matter as efficiently as physically possible. Under normal circumstances, supermassive black holes feed through a complex ecosystem involving star formation, stellar death, and gravitational interactions that drive gas inward over millions of years. Dying stars provide heavy elements that help cool interstellar gas, making it easier for material to lose energy and spiral toward the central black hole. But QSO-1 appears to be feeding without this normal stellar support system. The pristine chemical environment actually makes efficient feeding more difficult rather than easier, confirmed through theoretical modeling studies. Hot gas clouds dominated by hydrogen and helium have limited cooling mechanisms, making it harder for material to lose the thermal energy necessary to fall inward under gravity. Yet somehow, QSO-1 has managed to maintain feeding rates close to the theoretical maximum despite these challenges. One possibility is that the black hole feeds through direct accretion of primordial gas clouds that never had a chance to form stars. In the dense environment of the early universe, dark matter structures could have concentrated enough material to feed supermassive black holes directly without requiring the complex stellar processing that characterizes modern systems. This cold accretion mode might explain the unusual feeding signatures we observe. Alternative feeding mechanisms could involve the interaction between multiple massive objects in the early universe. If QSO-1 formed through the merger of smaller primordial black holes, the gravitational disruption from these events could have stirred up surrounding matter and driven it inward at accelerated rates. The feeding frenzy we observe might be the aftermath of such merger activity. The feeding signatures also provide clues about the black hole's rotation state and magnetic field configuration. The specific patterns of emission lines suggest complex gas dynamics that extend far beyond the simple circular orbits assumed in basic accretion models. These observations hint at sophisticated feeding mechanisms operating under conditions never observed in the modern universe. But what comes next reveals an even stranger aspect of how these cosmic monsters operate in the primordial cosmos. Every black hole in the universe faces a fundamental speed limit that governs how quickly it can grow. Named after British astrophysicist Arthur Eddington, this limit describes the maximum rate at which any massive object can consume matter before its own feeding process becomes self-defeating. The radiation generated by infalling material becomes so intense that it literally blows away incoming fuel, starving the black hole just when it should be growing fastest. The physics behind this limit involves a delicate balance between gravity pulling matter inward and radiation pressure pushing it outward. As gas spirals toward a black hole, gravitational friction heats it to millions of degrees, causing it to shine with the luminosity of billions of stars. This radiation carries momentum, and when the feeding rate becomes too high, the outward pressure from photons overwhelms the inward pull of gravity, shutting down the accretion process completely. For a 50 million solar mass black hole like QSO-1, the Eddington limit allows consumption of roughly 1 solar mass worth of material per year. This might sound like an enormous feeding rate, but it creates serious problems for explaining how such massive objects could have formed so early in cosmic history. Even feeding continuously at this maximum rate since the Big Bang, QSO-1 could have grown to only a fraction of its observed mass. The timeline calculations are unforgiving and mathematically precise. Starting from a typical stellar mass black hole weighing 100 solar masses, continuous feeding at the Eddington limit for 700 million years could produce an object weighing at most 10 million solar masses. To reach QSO-1's 50 million solar mass scale requires either much longer time periods or feeding rates that violate fundamental physics. Some theoretical models propose that black holes in the early universe could have exceeded the Eddington limit through super-Eddington accretion, consuming matter faster than the radiation pressure should allow. But these scenarios require very specific environmental conditions that may not have existed in the pristine gas clouds surrounding QS01. The low metallicity environment lacks the opacity needed to shield accreting material from its own radiation. Alternative growth mechanisms involve mergers between smaller black holes, potentially allowing rapid mass accumulation without violating the Eddington limit for individual objects. But merger-driven growth faces its own timing problems, requiring pre-existing populations of intermediate mass black holes that themselves needed time to form and find each other in the sparse early universe environment. The Eddington limit problem becomes even more severe when we consider that QS01 appears to be operating near this maximum feeding rate right now. The observed luminosity suggests ongoing accretion at close to the theoretical boundary, meaning the black hole is currently consuming matter as fast as physics allows. How could it have sustained such extreme feeding rates for hundreds of millions of years without exhausting its fuel supply? The answer may require abandoning conventional assumptions about how matter behaves around massive black holes in exotic environments. The formation mystery of QS01 has crystallized into a fundamental debate between two competing theories that represent completely different pathways for building supermassive black holes in the early universe. The light seed theory proposes that stellar mass black holes weighing tens of solar masses served as the foundation for gradual growth over cosmic time. The heavy seed theory suggests that much more massive objects weighing thousands to millions of solar masses formed directly, providing a head start that could explain early universe monsters. Light seed formation follows the conventional stellar evolution pathway that operates throughout the modern universe, confirmed through extensive observations of stellar populations. The first generation of stars in the universe were massive giants that burned through their nuclear fuel in just a few million years, before collapsing into black holes weighing between 10 and 100 solar masses. These stellar remnants then served as seeds for subsequent growth through accretion and mergers. The light seed pathway faces severe timing constraints when applied to objects like QS01. Even under the most optimistic growth scenarios, building a 50 million solar mass black hole from a 100 solar mass seed requires feeding at maximum rates for hundreds of millions of years. The process demands a constant supply of fuel and perfect feeding efficiency that may not have been possible in the sparse early universe environment. Mathematical modeling of light seed growth shows that most scenarios fall short of explaining the most massive early universe black holes by factors of 10 or more. The objects simply don't have enough time to reach the observed masses through conventional stellar origin pathways, even when accounting for optimistic assumptions about feeding rates and merger frequencies. Heavy seed theory proposes a radically different formation mechanism, where much more massive objects form directly from primordial conditions. These heavy seeds could weigh anywhere from 10,000 to 1 million solar masses, providing a substantial head start that makes rapid growth to supermassive scales mathematically feasible within the available time constraint. Direct collapse represents the most promising heavy seed formation mechanism, involving the gravitational collapse of massive pristine gas clouds without fragmentation into individual stars. Under very specific conditions in the early universe, clouds weighing millions of solar masses could have remained stable long enough for gravity to overcome internal pressure and trigger direct black hole formation. But heavy seed formation requires exotic conditions that may have been rare in the early universe. The gas clouds must remain free of heavy elements that would allow cooling and fragmentation, while simultaneously avoiding disruption by nearby stellar activity or merger events. These requirements create a narrow window of opportunity that may not have operated frequently enough to explain the abundance of early massive black holes. Primordial black hole formation represents another heavy seed pathway that bypasses stellar processes entirely. These objects could have formed during the first microseconds after the Big Bang from quantum density fluctuations, emerging as fully formed black holes with masses determined by the initial conditions rather than subsequent evolution. The observational evidence from QSO, one may finally determine which formation pathway actually operated in the infant universe. Beyond the missing ultraviolet radiation, QSO-1 presents astronomers with another baffling mystery that challenges fundamental assumptions about how active black holes operate. Every known feeding supermassive black hole in the modern universe blazes with intense X-ray emission, creating some of the brightest sources of high-energy radiation in the cosmos. Yet when astronomers point their most sensitive X-ray telescopes toward QSO-1 and other little red dots, they find mostly silence where theory predicts a brilliant cosmic lighthouse. X-ray emission represents one of the most reliable signatures of black hole activity, confirmed through decades of observations using space-based X-ray observatories. When matter falls toward a black hole, it forms an accretion disk that heats up to temperatures exceeding 10 million degrees through gravitational friction. At these extreme temperatures, atoms lose their electrons completely, creating a plasma that radiates primarily in X-ray wavelengths. The intensity of X-ray emission directly correlates with the black hole's feeding rate, providing astronomers with a powerful diagnostic tool for measuring accretion activity across cosmic distances. More feeding means more X-rays, following predictable relationships that have been calibrated through thousands of observations of active galactic nuclei in the nearby universe. But QSO-1 defies these established patterns completely. Despite showing clear evidence of ongoing accretion through its broad hydrogen emission lines and extreme luminosity, the object produces X-ray emission far weaker than expected for its apparent feeding rate. Some little red dots show no detectable X-ray emission at all, earning them the designation of X-ray weak active galactic nuclei. This X-ray deficiency cannot be explained by simple absorption effects, where intervening material blocks the high-energy radiation before it reaches our telescopes. The pristine environment around QSO-1 contains insufficient dust or gas to absorb X-rays completely, and absorption would create characteristic spectral signatures that are not observed in the available data. Alternative explanations involving unusual accretion geometries have been proposed, but struggle to account for the complete absence of X-ray emission in some objects. Even the most exotic feeding configurations should produce some detectable high-energy radiation, yet multiple independent observations using different X-ray telescopes have failed to detect significant emission from many little red dots. The X-ray silence becomes even more puzzling when we consider that some little red dots do show detectable X-ray emission, while others appear completely quiet despite having similar optical and infrared properties. This inconsistency suggests that multiple classes of objects may be masquerading as similar phenomena, each operating according to different physical principles. One possibility is that the X-ray emission is being suppressed by magnetic fields or radiation pressure effects that don't operate in modern black hole systems. The extreme conditions in the early universe, combined with the unusual mass ratios and pristine environments, might allow accretion processes that avoid the high-temperature plasma formation responsible for X-ray production. This radiation mystery points toward fundamental differences between ancient and modern black hole feeding mechanisms. The discovery of QSO-1 wouldn't have been possible without one of Einstein's most profound predictions coming to our rescue across 13 billion years of cosmic history. Gravitational lensing, the bending of light by massive objects, has transformed a barely detectable ancient speck into a cosmic magnifying glass that reveals secrets hidden since the universe's infancy. This natural telescope effect represents humanity's most powerful tool for studying the earliest epochs of cosmic evolution. Einstein's general theory of relativity, published over a century ago, predicted that massive objects would warp the fabric of spacetime itself, causing light rays to follow curved paths rather than straight lines. This effect becomes most pronounced around the most massive structures in the universe, such as galaxy clusters containing trillions of times the mass of our Sun, concentrated into relatively small cosmic volumes. The galaxy cluster, acting as our cosmic telescope, sits roughly halfway between Earth and QSO-1, at just the right position to create what astronomers call a strong gravitational lens. The cluster's immense gravity bends light from the background object, focusing it like a giant cosmic magnifying glass and amplifying the brightness by factors of 10 or more. Without this fortunate alignment, QSO-1 would remain invisible to even our most powerful telescopes. But gravitational lensing does more than just make distant objects brighter. The effect also creates multiple images of the same background source, each showing the object from slightly different angles and at different times. Light, taking different paths around the lensing cluster, arrives at Earth at different moments, providing a unique window into how the distant object changes over time. This time delay effect has revealed crucial information about QSO-1's variability and feeding behavior. By comparing the brightness changes in different lensed images, astronomers can study how the accretion process operates around the supermassive black hole, measuring feeding rates and detecting subtle changes that would be impossible to observe at such extreme distances without lensing magnification. The lensing also acts as a natural spectrometer, stretching and magnifying the light from QSO-1 enough to allow detailed spectroscopic analysis of its chemical composition and gas dynamics. The rotation curve measurements that confirmed the 50 million solar mass central object were only possible because gravitational lensing provided sufficient light-gathering power to detect the subtle velocity shifts of orbiting gas, clouds. Beyond its practical benefits, gravitational lensing provides a direct demonstration of Einstein's most exotic predictions operating on cosmic scales. The precise bending angles observed in lens systems confirm general relativity to extraordinary precision, while simultaneously allowing us to map the distribution of dark matter in the lensing clusters themselves. The cosmic coincidence that placed a massive galaxy cluster exactly between Earth and one of the most interesting objects in the early universe represents an almost miraculous alignment. The probability of such perfect positioning occurring by chance is astronomically small, making QSO-1's discovery a testament to both cosmic fortune and human ingenuity in recognizing the significance of what we were seeing. This gravitational time machine has opened a window into cosmic epochs we never imagined we could study in such detail. The discovery of massive black holes like QSO-1 in the early universe has profound implications for one of modern cosmology's most pressing mysteries, the Hubble tension. This crisis involves conflicting measurements of how fast the universe is expanding, with different methods giving results that disagree by several percent. While this might sound like a small discrepancy, it represents a fundamental breakdown in our understanding of cosmic evolution that could require revolutionary changes to the standard model of cosmology. The Hubble tension arises from comparing expansion rate measurements using nearby supernovae versus calculations based on the cosmic microwave background, that ancient light from just 380,000 years after the Big Bang. Local measurements consistently give higher expansion rates than predictions based on early universe observations, creating a disagreement that has persisted despite increasingly precise measurements from multiple independent research groups. Early universe black holes like QSO-1 could help resolve this tension by revealing that cosmic evolution proceeded much more rapidly than standard models predict. If massive structures formed earlier and grew faster than expected, it could indicate that the universe expanded at different rates during its early epochs, potentially reconciling the conflicting measurements through more complex evolutionary scenarios. The abundance of little red dots and massive early black holes suggests that the infant universe was far more active and structured than theoretical models allow. Standard cosmology predicts a relatively smooth early universe, where large structures formed gradually through hierarchical assembly over billions of years. But the discovery of 50 million solar mass black holes, just 700 million years after the Big Bang, indicates that cosmic evolution operated much more efficiently than we believed. This accelerated early evolution could affect the cosmic expansion history in subtle ways that influence how we interpret distance measurements to remote objects. If the universe went through periods of enhanced structure formation or different expansion rates, it could create systematic errors in the cosmic distance ladder that underlies local expansion rate measurements. Additionally, massive early black holes could have influenced the cosmic microwave background itself through their gravitational effects and energy injection into the primordial plasma. These influences could alter the acoustic signatures used to calibrate cosmological parameters, potentially explaining why early universe measurements disagree with local observations. The energy output from early supermassive black holes could also have affected the reionization process that transformed the universe from a dark, neutral state to the transparent cosmos we observe today. Changes to the reionization timeline could alter how light from distant objects reaches us, creating additional systematic effects in cosmological measurements. Some theoretical models propose that primordial black holes could provide the missing dark matter component that makes up roughly 25% of the universe's mass-energy budget. If objects like QSO-1 represent a previously unrecognized population of primordial black holes, they could help resolve chemical enrichment and galaxy formation during the cosmos's first billion years. The technique of stellar archaeology relies on the fact that different elements produce characteristic absorption and emission lines at specific wavelengths, confirmed through laboratory experiments and theoretical calculations. When light from QSO-1 passes through intervening gas clouds or originates from stellar populations in its vicinity, these atomic signatures become imprinted in the spectrum, creating a detailed chemical census of the early universe environment. The oxygen abundance measurements that revealed QSO-1's pristine environment represent just one aspect of this cosmic archaeological investigation. Detailed spectroscopic analysis can detect dozens of different elements, each telling part of the story about what types of stars lived and died in the region during the universe's first few 100 million years. The absence of certain elements is often as informative as their presence. Carbon signatures provide particularly important clues about early stellar populations because this element is produced primarily by intermediate mass stars during their asymptotic giant branch phase. The carbon-to-oxygen ratio in ancient gas clouds reveals whether the first stars followed similar evolutionary pathways to modern stellar populations or operated under fundamentally different physics due to the exotic conditions of the primordial universe. Nitrogen abundance offers another crucial diagnostic because this element is produced through secondary nucleosynthesis processes that require multiple generations of stellar evolution. High nitrogen levels indicate that several stellar generations have lived and died in a region, while low nitrogen abundance suggests minimal stellar processing, consistent with what we observe around QSO-1. The isotope ratios of various elements provide even more detailed information about the nuclear physics operating in the first stars. Different isotopes are produced by different stellar masses and evolutionary phases, allowing astronomers to reconstruct not just whether stars formed, but what types of stars dominated the early universe and how they differed from modern stellar populations. Iron peak elements like iron, nickel, and cobalt are produced primarily during supernova explosions, providing direct evidence for the violent death of massive stars. The specific patterns of these elements can distinguish between different types of supernovae, revealing whether the first stellar explosions followed the same patterns we observe in the nearby universe or represented a unique class of primordial phenomena. Perhaps most intriguingly, the search for lithium signatures in early universe objects could provide tests of Big Bang nucleosynthesis predictions. Lithium-7 was produced during the first few minutes after the Big Bang, but stellar processing typically destroys this fragile isotope. The abundance patterns around objects like QSO, one could reveal whether primordial lithium production matched theoretical expectations or required modifications to our understanding of cosmic nucleosynthesis. This archaeological evidence is rewriting the biography of the universe's first billion years. While QSO-1 represents the most extreme example of early universe black hole mysteries, it's not alone in its cosmic neighborhood. The gravitational lens that revealed this naked monster also exposed an even more extraordinary system, a triple black hole configuration where three separate supermassive objects coexist within a single gravitational environment. This discovery provides unprecedented insight into how massive black holes interacted and merged during the universe's most chaotic early epochs. The system consists of QSO-1 itself plus two additional supermassive black holes located in the cores of merging galaxies, positioned nearby in the same lensed field of view. Each of these objects weighs millions of times more than our Sun, creating a gravitational dance of unprecedented complexity in the early universe. The three monsters are caught in the act of what may become the most massive black hole merger event ever observed. Computer simulations of triple black hole systems reveal dynamics far more complex than simple two-body mergers, confirmed through detailed gravitational wave calculations. When three massive objects interact gravitationally, the system becomes chaotic, with objects following unpredictable orbital paths that can eject one member entirely or lead to spectacular collision events that release energy equivalent to billions of supernovae. The discovery of this triple system provides direct observational evidence for the hierarchical merger processes that theoretical models predict should have operated in the dense early universe. When cosmic structures were more compact and collisions more frequent, multiple massive black holes could have found themselves in close proximity, leading to complex gravitational interactions that helped build the most massive objects we observe today. Gravitational wave observatories like LIGO and Virgo have detected dozens of black hole mergers in the nearby universe, but these events typically involve stellar mass objects weighing tens of solar masses. The QSO-1 triple system represents mergers on scales thousands of times more massive, potentially producing gravitational wave signals unlike anything yet observed by current detectors. The timing of these mergers could help explain how supermassive black holes reached extreme masses so early in cosmic history. Instead of growing gradually through gas accretion over billions of years, massive black holes could have achieved rapid growth spurts through merger events that combined multiple pre-existing objects into even more massive monsters within relatively short time periods. But triple black hole systems also create unique observational challenges that complicate our understanding of early universe evolution. The gravitational interactions between multiple massive objects can disrupt normal accretion processes, potentially explaining some of the unusual radiation signatures observed in little red dots. The complex dynamics could also affect the chemical evolution of surrounding gas, altering the stellar archaeology evidence used to reconstruct early cosmic history. The energy injection from multiple active black holes in close proximity could have profound effects on galaxy formation and evolution in the surrounding region. The combined radiation output and gravitational disruption might prevent normal star formation, while simultaneously feeding the black holes through tidal disruption of surrounding material. This triple monster system reveals that the early universe was even more violent and chaotic than we ever imagined. The chemical composition of gas surrounding early universe, black holes like QSO-1, holds the key to understanding how the first stellar populations differed from anything we observe in the modern cosmos. Astronomers use the term metallicity to describe the abundance of elements heavier than hydrogen and helium, and the metallicity patterns around ancient objects reveal a story of stellar evolution operating under conditions that no longer exist anywhere in the universe. In astronomical terminology, everything heavier than hydrogen and helium counts as a metal, regardless of its chemical properties. This includes crucial elements like carbon, nitrogen, oxygen, and iron that play essential roles in stellar evolution, planet formation, and ultimately the development of life itself. The metallicity of a region provides a direct measurement of how much stellar processing has occurred there over cosmic time. The pristine environment around QSO-1, with metallicity less than 1% of solar values, represents one of the most chemically primitive regions ever discovered in the universe. This extreme metal deficiency indicates that very few massive stars have lived and died in this region. Despite the system existing for over 700 million years in a dense early universe environment where star formation should have been vigorous. But the metallicity mystery extends beyond just the overall abundance of heavy elements to the specific ratios between different chemical species. The early universe should have been dominated by what astronomers call population, 3 stars, massive giants with essentially zero metallicity that operated according to different physics than any stars we can observe today. These primordial giants would have produced distinctive elemental signatures when they died. Population. 3 supernovae are predicted to create very different abundance patterns than modern stellar explosions, confirmed through detailed nucleosynthesis calculations. They should produce enhanced ratios of certain alpha elements, like oxygen, neon, and magnesium, compared to iron peak elements, creating chemical fingerprints that could be detectable in the gas around early universe objects. Yet, the metallicity patterns observed around QSO-1 and other little red dots don't clearly match population 3 predictions, suggesting either that these first stars were rarer than expected or that they operated differently than theoretical models predict. The absence of characteristic population 3 signatures represents a major puzzle in our understanding of early cosmic chemical evolution. Alternative explanations involve chemical mixing processes that could have homogenized the primordial gas before substantial star formation occurred. If early universe turbulence was more efficient at mixing chemical products than modern processes, it could have diluted and redistributed the signatures of first-generation stellar evolution, creating the smooth metallicity patterns we observe. The metal deficiency could also result from active removal processes operating around massive black holes. If QSO-1 formed early and began feeding immediately, its radiation output could have heated and ionized surrounding gas, preventing the gravitational collapse necessary for efficient star formation, while simultaneously driving away enriched material through powerful outflows. These chemical archaeological clues suggest that stellar evolution in the early universe followed pathways we've never observed before. QSO-1 exists during one of the most dramatic transformations in cosmic history, the epoch of reionization, when the universe underwent a fundamental phase transition from darkness to light that permanently altered the properties of space itself. Understanding how massive black holes like QSO-1 influence this cosmic metamorphosis provides crucial insight into how the modern universe acquired the transparent properties that allow galaxies, stars, and planets to form and evolve. For roughly 400 million years after the Big Bang, the universe existed in a state astronomers call the Dark Ages. During this period, space was filled with neutral hydrogen atoms that absorbed virtually all ultraviolet and visible light, making the cosmos completely opaque. No stars had yet formed to illuminate the darkness, and the only source of energy was the gradually cooling afterglow of the Big Bang itself. The first stars finally ignited around 100 million years after cosmic dawn, but these initial stellar populations were insufficient to transform the universe's fundamental properties. It took hundreds of millions of years of stellar evolution, supernovae explosions, and the formation of the first galaxies before enough high-energy radiation accumulated to begin ionizing the intergalactic medium on large scales. Reionization represents the process by which this neutral hydrogen was stripped of its electrons, transforming space from an opaque fog into the transparent medium we observe today. This transformation required enormous amounts of high-energy radiation, primarily ultraviolet photons, energetic enough to ionize hydrogen atoms and keep them ionized against the tendency to recombine into neutral states. Massive black holes like QSO-1 could have played a crucial role in driving reionization through their intense radiation output. A 50 million solar mass black hole feeding at near Eddington rates produces ultraviolet luminosity equivalent to billions of massive stars, creating spheres of ionized gas extending across millions of light years. These ionization bubbles could have been instrumental in completing the reionization process, but the radiation signatures we observe from QSO-1 and other little red dots don't match the expected ultraviolet output needed for efficient reionization, creating another layer of mystery in understanding early cosmic evolution. If these objects were responsible for reionization, they must have produced their ionizing radiation through processes that differ significantly from modern black hole activity. The timing of reionization completion, measured through observations of the cosmic microwave background and distant quasars, suggests the process finished by roughly 1 billion years after the Big Bang. QSO-1, existing at 700 million years post-Big Bang, represents an object caught during the final stages of this cosmic transformation. The environment around QSO-1 provides direct observational evidence for reionization conditions, with ionized gas signatures indicating that the surrounding medium had already been processed by high-energy radiation. This ionized environment may have been crucial for allowing the black hole to feed efficiently, as neutral hydrogen would have provided additional opacity that could have interfered with accretion processes. The reionization epoch reveals how objects like QSO-1 helped create the transparent universe we inhabit today. The discovery of QSO-1 represents just the beginning of a revolution in our understanding of the early universe that will unfold over the coming decades as JWST continues pushing the boundaries of observable cosmic history. Current observations have revealed the tip of an iceberg of early universe mysteries, with hundreds of additional little red dots waiting for detailed analysis and potentially thousands more hiding at the limits of detectability. JWST's unprecedented infrared capabilities allow it to observe objects at redshifts beyond anything accessible to previous telescopes, confirmed through spectroscopic measurements that push back the frontier of observable cosmic time. Each additional year of observations extends our view deeper into the past, revealing epochs of cosmic evolution that remained completely hidden until recently. The telescope's systematic surveys of large sky areas are already uncovering little red dots at an accelerating pace, with new discoveries announced almost monthly as analysis of archival data continues. Statistical studies of these populations will reveal whether objects like QSO-1 represent rare cosmic accidents or common features of early universe evolution that demand fundamental revisions to cosmological models. Future observations will target the most extreme examples for detailed spectroscopic follow-up, measuring precise masses, chemical compositions, and feeding rates for dozens of early universe black holes. These measurements will test whether the formation mechanisms proposed for QSO-1 apply broadly to the entire population, or whether multiple pathways operated simultaneously during cosmic dawn. The next generation of extremely large ground-based telescopes, with mirrors 30 to 40 meters in diameter, will provide unprecedented light-gathering power for studying the faintest early universe objects. These facilities will detect stellar populations around early black holes with sensitivity levels impossible with current technology, potentially revealing the missing galactic components that surround naked monsters like QSO-1. Gravitational wave observatories, scheduled for the next decade, will directly detect the merger events that may have created supermassive black holes in the early universe. The laser interferometer space antenna will be sensitive to mergers involving million solar mass objects, providing direct observational evidence for the hierarchical assembly processes that theoretical models predict. Advanced computer simulations running on the next generation of supercomputers will model early universe evolution with unprecedented detail, incorporating the new physics revealed by observations of objects like QSO-1. These simulations will test formation scenarios and predict the observable signatures of different theoretical pathways, guiding future observational strategies. The chemical archaeology techniques pioneered in studying QSO-1 will be applied to hundreds of additional objects, building a comprehensive picture of stellar evolution during the first billion years of cosmic history. This database will reveal whether population 3 stars really dominated early stellar populations, or whether the first generation of stars followed completely different evolutionary pathways. Perhaps most excitingly, future observations may reveal the merger outcomes of systems like the triple black hole configuration discovered around QSO-1, showing how the most massive objects in the universe assembled through violent gravitational interactions. The cosmic mysteries revealed by QSO-1 are just the beginning of discoveries that will reshape our understanding of reality itself. The accumulating evidence from QSO-1 and hundreds of other early universe discoveries has created a fundamental crisis in cosmological theory that threatens to overturn decades of carefully constructed models for cosmic evolution. The timeline simply doesn't add up. Massive black holes weighing tens of millions of solar masses shouldn't exist just 700 million years after the Big Bang. Yet, JWST observations confirm their presence with mathematical certainty. This timeline crisis extends far beyond individual objects to challenge the entire framework of hierarchical structure formation that underlies modern cosmology. The Standard Model predicts a universe where small structures form first and gradually merge to build larger objects over billions of years. But early massive black holes suggest that some of the universe's most extreme objects formed essentially instantly on cosmic timescales. The mathematical constraints are unforgiving and have been verified through multiple independent analysis methods. Starting from any reasonable initial conditions in the early universe, conventional formation processes simply cannot build 50 million solar mass black holes within the available time. The growth rates required exceed fundamental physical limits by factors of 10 or more, making these objects impossible according to established physics. This impossibility has forced theorists to propose increasingly exotic formation mechanisms that operate outside the boundaries of well-tested physics. Primordial black holes formed during the Big Bang itself represent one possibility, but these objects require very specific inflation scenarios that most cosmic models don't naturally produce. The abundance of early massive black holes suggests formation mechanisms far more efficient than any standard theory allows. Direct collapse scenarios face their own theoretical challenges, requiring environmental conditions that may have been extremely rare in the early universe. The pristine chemical compositions and specific density profiles needed for direct collapse create such narrow windows of opportunity that most models predict far fewer massive early black holes than observations reveal. The crisis has prompted some researchers to question whether our fundamental understanding of gravity itself might be incomplete. Modified gravity theories that alter the strength of gravitational attraction in the early universe could potentially allow faster structure formation and black hole growth. But these modifications typically create conflicts with other well-established cosmological observations. Alternative solutions involve revising our understanding of dark matter properties or the expansion history of the universe itself. If dark matter interactions were stronger in the early universe, or if cosmic expansion proceeded differently than current models predict, it might allow the accelerated structure formation needed to explain early massive black holes. The timeline crisis also affects our understanding of galaxy formation, star formation efficiency, and the chemical evolution of the universe. If massive black holes really did form before their host galaxies, then the entire sequence of cosmic structure assembly needs revision, with black holes playing a much more fundamental role in shaping cosmic evolution than previously realized. Recent attempts to resolve the crisis through hybrid formation scenarios that combine multiple pathways have shown some promise, but struggle to match the detailed observational properties of objects like QS01. The extreme mass ratios, chemical compositions, and radiation signatures require very specific formation histories that remain difficult to explain through any single theoretical framework. The crisis demands either revolutionary new physics or fundamental revisions to our understanding of cosmic evolution. As we stand at the threshold of cosmic discoveries that challenge everything we thought we knew about the universe's formation and evolution, QS01 and its fellow monsters force us to confront profound questions about our place in a cosmos far stranger and more violent than we ever imagined. These naked black holes from the universe's infancy reveal that the cosmos has always been This revelation carries profound implications for the development of life itself throughout cosmic history. If massive black holes really did form before their host galaxies, then the radiation environments during the universe's first billion years were far more intense than theoretical models predicted. The high energy output from early supermassive black holes could have sterilized vast regions of space, preventing the chemical evolution necessary for planet formation and biological development. Yet, paradoxically, these same monsters may have been essential for creating the conditions that eventually allowed life to emerge. The gravitational influence of supermassive black holes helps regulate star formation in galaxies, preventing runaway stellar production that could consume all available gas too quickly. The feedback between black hole activity and galaxy evolution creates the stable, long-lived stellar populations that provide the billions of years of stable energy output necessary for biological evolution. The pristine chemical environments we observe around objects like QS01 represent cosmic laboratories, where we can study the universe's fundamental properties in their most primitive state. These regions preserve conditions that existed during cosmic dawn, offering unique insight into the physics that operated when space itself was young and the laws of nature operated under extreme conditions never again repeated in cosmic history. The abundance of early universe monsters also affects our calculations of how common intelligent life might be throughout the cosmos. If supermassive black holes were more active and numerous during the universe's first few billion years, then the habitable zones around stars may have been much smaller than we calculate based on modern conditions. The cosmic real estate suitable for life may have been vanishingly rare during the epochs when complex chemistry first became possible, but the universe's transition from monster-dominated chaos to the relatively peaceful cosmos we observe today also demonstrates the remarkable resilience of physical processes that eventually allowed complexity to emerge. Despite existing in an environment filled with radiation from feeding supermassive black holes, the universe still managed to cool sufficiently for atoms to form stable molecules, for gravity to assemble the first solid objects, and for chemistry to begin the long journey toward biological complexity. The naked black holes of the early universe serve as cosmic anchors that connect our local existence to the most extreme physics operating anywhere in space and time. Every atom in our bodies was forged in stellar cores that formed in galaxies whose evolution was shaped by the gravitational influence of supermassive black holes. We are literally made from material processed by cosmic monsters. In discovering QS01, we have found not just an impossible object, but a mirror reflecting our own cosmic origins in a universe stranger and more wonderful than we dared imagine. While JWST reveals the optical signatures of QS01 and its cosmic cousins, another revolutionary technology promises to detect the violent birth cries of these monsters through ripples in spacetime itself. Gravitational waves, those faint distortions in the fabric of reality predicted by Einstein and first detected in 2015, carry information about the most energetic events in cosmic history, including the formation and merger processes that may have created supermassive black holes in the infant universe. The Laser Interferometer Gravitational Wave Observatory has already detected dozens of black hole mergers in the nearby universe. But these events involve relatively lightweight objects weighing tens of solar masses. The gravitational waves from such mergers create detectable signals for only a few seconds as the objects spiral inward and collide. But mergers involving million solar mass objects like those surrounding QS01 would produce signals unlike anything yet observed. Supermassive black hole mergers generate gravitational waves with much lower frequencies than stellar mass events, confirmed through theoretical calculations of the orbital dynamics. These waves oscillate over periods of hours or days rather than milliseconds, requiring completely different detection strategies than current ground-based observatories can provide. The signals would be too low in frequency for LIGO's sensitivity range, but perfect for space-based gravitational wave detectors. The European Space Agency's Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will be specifically designed to detect these low-frequency gravitational waves from supermassive black hole mergers. The detector will consist of 3 spacecraft flying in formation across millions of kilometers, creating an interferometer larger than Earth's orbit that can sense space-time distortions from the most massive cosmic collisions. When LISA begins operations, it will provide direct observational evidence for the hierarchical merger processes that may have built objects like QS01. If early supermassive black holes formed through cascading mergers of smaller objects, LISA should detect dozens of these events each year, revealing the gravitational symphony that accompanied the universe's most violent epoch of structure formation. But the gravitational wave signatures could also distinguish between different formation mechanisms for early supermassive black holes. Primordial black holes formed during the Big Bang would have different merger statistics than objects built through stellar evolution or direct collapse processes. The merger rates, mass distributions, and orbital characteristics detected by LISA will test which formation theories actually operated in the early universe. Perhaps most excitingly, gravitational waves travel at the speed of light without interaction with matter, carrying information about events that occurred most extreme objects. Soon we may hear the actual sounds of cosmic monsters being born in the primordial darkness. The existence of naked supermassive black holes like QS01 has reopened one of cosmology's most fundamental questions. What is the true nature of dark matter, that invisible substance that comprises 85% of all matter in the universe? The formation of massive black holes so early in cosmic history requires dark matter to behave in ways that challenge our current understanding of this mysterious cosmic component. Standard dark matter models describe particles that interact only through gravity, clumping together to form the invisible scaffolding upon which normal matter assembles into galaxies and stars. These cold dark matter models successfully explain large-scale cosmic structure, but struggle to account for how supermassive black holes could form so rapidly in the early universe, when dark matter halos were still relatively small and sparse. The pristine environment around QS01 provides crucial clues about dark matter behavior during cosmic dawn. If the black hole formed through conventional processes requiring pre-existing dark matter structures, we should observe evidence of substantial stellar populations that formed within the same dark matter halo. Yet QSO-1 appears essentially naked, suggesting formation mechanisms that bypassed normal structure formation entirely. One possibility is that dark matter itself played a more active role in early black hole formation than current models allow. If dark matter particles could interact with each other through forces beyond gravity, they might have been able to collapse directly into dense concentrations, massive enough to form supermassive black holes without requiring normal matter as an intermediary. Self-interacting dark matter models propose that dark matter particles can collide and exchange energy, allowing dark matter structures to collapse more efficiently than purely gravitational processes would permit. Under the right conditions, such interactions could have triggered the formation of massive dark matter clumps that subsequently collapsed into primordial black holes weighing millions of solar masses. Alternative theories suggest that dark matter might not be composed of particles at all, but could instead consist of primordial black holes formed during the Big Bang's first moments. If a significant fraction of dark matter exists as black holes weighing thousands to millions of solar masses, it could explain both the missing matter problem and the early formation of supermassive objects like QSO-1. The primordial black hole dark matter hypothesis faces observational constraints from gravitational microlensing studies and cosmic microwave background measurements, but these constraints still allow substantial populations of intermediate mass primordial black holes. Recent calculations suggest that primordial black holes in the million solar mass range could constitute a significant fraction of dark matter without violating existing observational limits. The gravitational effects of dark matter around QSO. One could provide direct tests of these competing theories through precise measurements of mass distributions and orbital dynamics. If the system contains substantial amounts of primordial black hole dark matter, it should show characteristic signatures in the rotation curves and gravitational lensing properties that differ from conventional dark matter predictions. Future observations with next-generation telescopes will map dark matter distributions around early universe objects with unprecedented precision, potentially revealing whether dark matter behaves according to standard models or requires exotic physics to explain the rapid formation of cosmic monsters. The naked black holes of the early universe may hold the key to solving the dark matter mystery itself. The extreme physics operating around QSO-1 forces us to confront a mind-bending possibility that time itself flowed differently in the early universe, operating under conditions so exotic that our conventional understanding of causality, simultaneity, and temporal flow may not apply to cosmic dawn. The formation timelines that make objects like QSO-1 impossible under current physics might become feasible if time itself evolved along with the expanding cosmos. Einstein's general relativity reveals that time is not the universal constant our everyday experience suggests, but rather a flexible dimension that can stretch, compress, and curve in response to gravitational fields and cosmic expansion. In the extreme gravitational environments surrounding supermassive black holes, time dilation effects become so pronounced that events near the black hole appear to unfold in slow motion when viewed from distant locations. But the early universe presented gravitational conditions far more extreme than anything existing today, confirmed through calculations of cosmic density evolution. When the universe was just 700 million years old, the average density of matter was over 1,000 times higher than current values, creating gravitational fields that permeated all of space rather than being localized around individual massive objects. This high-density environment could have created universe-wide time dilation effects that fundamentally altered the pace of physical processes during cosmic dawn. Events that appear to require impossible timelines when viewed from our current low-density cosmic environment might have unfolded at accelerated rates in the gravitationally intense conditions of the early universe. Theoretical calculations of time flow in expanding cosmological models reveal that the relationship between coordinate time and proper time becomes increasingly complex in high-density epochs. What we measure as 700 million years of cosmic evolution might represent much longer periods of proper time for physical processes operating in the early universe's intense gravitational environment. Additionally, the cosmic expansion itself affects the flow of time through the universe's changing geometry and curvature. During the epoch when QS01 formed, spacetime curvature was much more pronounced than today, potentially creating temporal environments where rapid structure formation became physically possible through mechanisms that no longer operate in our flattened modern cosmos. Quantum mechanical effects during cosmic inflation could have established initial conditions that fundamentally altered temporal evolution throughout subsequent cosmic history. If the early universe underwent periods of accelerated expansion or contraction, it could have compressed the effective timelines available for structure formation, while maintaining consistency with our observations of cosmic age and evolution. The extreme redshift of QS01 means we observe this object through a cosmological lens that transforms both spatial and temporal coordinates. The light we detect has been stretched and altered by 13 billion years of cosmic expansion, potentially masking temporal effects that operated during the object's formation epoch, but no longer influence cosmic evolution. Recent theoretical work in quantum gravity suggests that spacetime itself might have possessed different fundamental properties during the universe's earliest moments, when quantum effects dominated over classical general relativity. These quantum spacetime effects could have allowed rapid structure formation through processes that become impossible once classical spacetime geometry was established. If time itself was different during cosmic dawn, then the impossible monsters of the early universe become evidence of physics beyond our current understanding. As our journey through the mysteries of QS01 reaches its conclusion, we find ourselves confronting a truth that extends far beyond the discovery of a single impossible object in the distant cosmos. This naked monster floating in primordial space represents the visible tip of a cosmic iceberg that challenges everything we thought we knew about the universe's fundamental nature, forcing humanity to accept that reality operates on scales and through mechanisms that dwarf our earthly intuitions about how existence itself works. The 50 million solar mass black hole that shouldn't exist has become a cosmic Rosetta Stone that deciphers messages written in the language of extreme physics during the universe's violent infancy. Every photon of ancient light from QS01 carries information about conditions so exotic that they required the universe itself to serve as a laboratory for experiments that could never be reproduced under any earthly conditions. What began as a tiny red dot in JWST's infrared vision has evolved into definitive proof that the cosmos we inhabit emerged from chaos, far more profound and creative than human imagination ever conceived. The pristine gas clouds, the impossible formation timelines, the missing radiation signatures, and the extreme mass ratios all point toward the same inescapable conclusion. The universe's first billion years operated according to physics that transcends our current understanding of reality. The implications cascade through every aspect of cosmic evolution, from the nature of dark matter and the expansion of spacetime to the fundamental properties of gravity and the flow of time itself. QS01 doesn't just represent an unusual object requiring minor theoretical adjustments, but evidence of a cosmos whose deepest laws remain hidden from our current scientific frameworks. Perhaps most remarkably, this monster black hole reveals that impossibility itself might be an illusion created by our limited perspective on cosmic history. What appears impossible when viewed through the lens of modern physics becomes inevitable when we acknowledge that the universe spent its formative years operating under conditions that no longer exist anywhere in observable space. The naked supermassive black holes, scattered throughout the early universe, serve as cosmic fossils, preserving evidence of creation's most dramatic moments, when reality itself was young enough that the fundamental forces operated through mechanisms we can barely begin to imagine. They represent living connections to the actual moment of cosmic birth, when the laws of physics were written in letters of fire across scales that encompass entire galaxies. Every technical measurement, every spectroscopic analysis, and every theoretical calculation surrounding QSO, one points toward the same profound realization. We inhabit a universe far stranger, more violent, and more creative than human consciousness evolved to comprehend. The cosmos doesn't just contain mysteries waiting to be solved through better observations and more sophisticated theories. It contains mysteries that require us to expand our fundamental conception of what reality means. As JWST continues peering deeper into cosmic history and revealing more impossible objects from the universe's infancy, we stand at the threshold of discoveries that will transform human understanding as profoundly as the recognition that Earth orbits the Sun rather than serving as the center of creation. The monsters of the early universe are calling to us across 13 billion years of space and time, carrying messages about the true nature of existence itself. In finding QSO 1, we have discovered not just a cosmic impossibility, but a mirror reflecting the infinite creative power of a universe whose deepest secrets we are only beginning to glimpse.